expertise is to translate the implications of findings of science and developments in technology into workable and cost-effective policy options for the states in the Northeast. Since 2003, he has been acting as a co-principal investigator at NESCAUM in a joint effort with the Georgia Institute of Technology and MIT on a policy-relevant research project that is evaluating future impacts of global climate change on regional air quality in the U.S., specifically ozone and fine PM, and I'm certain he'll draw upon that work in his talk today. Before joining NESCAUM, Dr. Amar was one of us. He was at the California Air Resources Board for 15 years, left in 1992. While he was here, he managed programs on air pollution research, including acid deposition, atmospheric processes, and ecological effects. He was also involved in strategic planning and industrial source pollution control. For over 10 years, he has been part-time faculty member at the University of California, Davis, California State University, Sacramento, and Tufts University in Boston. So he has good, strong academic roots. In addition, his PhD came from the University of California, Los Angeles. Please welcome Dr. Praveen Amar for this morning's seminar. Praveen.
Thank you. Thanks a lot. Thank you. First, I want to thank Bob Sawyer for inviting me, and thank you, ARB, for asking me to come back after 14 years. But I have been here a number of times for other purposes, but first time to give a talk. I'm going to talk about, as the panel shows there, and what Bob mentioned earlier, work we have been doing about for 3 years. Effect of global climate change on a larger scale to what happens at the ground level. You know, you hear about coastal floodings and other things, but simply air pollution issues, what happens to ozone at the ground level in the context of SIP and planning for PM2.5, and what happens across the whole country as a region, and then what happens to different parts of the country. So that's really the focus of my talk. And there are many people here. You can see the names behind at Georgia Tech. Ted Russell, whom many of you know, I'm sure. Ted Russell, he's the PI with me, and also MIT folks, Dr. Wang at the bottom, and a number of graduate students, and a number of people in our own office, Dr. Wu, Dr. Hay, and Emily, whose name doesn't appear there, Emily Savelli, so people working with me. So that's the effort. Also, it's funded by EPA. We are supposed to say that. It's funded by ORD under a STAR grant, which is the Science Assist. Thank you. Science to Achieve Results, STAR. Who are we? NESCAUM. I mean, you know, the key word there, I keep on telling people in NESCAUM, is the U word, the U's. Northeast States for Coordinated Air Use Management. First time when I saw that, I thought that's kind of an awkward word. But think about air as a resource, like we think about land use, water use. We don't think of air as a resource we use, but we do. Quite often we misuse it and abuse it, but we use it. And essentially you take good air and then you produce all kind of NOx and SO2 and other things. So think about how to manage the use of a resource, in this case air. And again, we are 8 states, and we've been there almost 40 years next year. And in the beginning we were working just for New England states, 6 New England states. There's a lot of cultural common points within the 6 New England states. That's 8 minus New York and New Jersey. And then New Jersey and New York joined later, and the trick was we still were NESCAUM. And instead of New England states, we became Northeast states, so we didn't have to change our long name. And here is the map. You can see there's a head at Maine, New York is tail, and you got states in between. And think about that as 8 states, 40 million people, and there's a lot of influence of that part, because unlike California, you have 1 governor, we have 8 governors. And we also have 16 senators. So politically, I think there's a lot of influence because of that, even though the number of people there are just as many as here. So in terms of the national policy, we kind of are a key player on issues from automobiles to acid rain, now global climate change. And our mission, I wrote down 5 things. We provide assistance to our states, technical kind, policy kind, We represent states in all kinds of national forums, CASAC, FACA process. Every time EPA needs states to kind of help them about the right policy with respect to mercury or other things, we sit on national forums. And the fourth one really is what I'm here for. That is, look at the issues which are not totally on the radar screen yet, but the emerging issues, but you got to see what might occur 5, 10, 20 years from now. And global climate change is one of those issues where states are, finally, I guess, focusing, but it's not the same way as SOx and NOx or PM or ozone, but that's where we come in. And finally, we provide states. All 8 states don't get along with each other all the time very well, so there's conflicts. We try to resolve our interstate conflicts among ourselves. We're a group of about 19 professional people, altogether 25 plus or so. The way we work, we have lots of committees. We got committees where the states sit on our committee, Station Source Committee, Mobile Source Committee, Global Climate Change Committee, and so on. So there's a lot of state participation, and that's where all the work gets done. States providing input to us, and then we're trying to put it together as a regional solution. People who might be interested in what we have done, we've done a lot of work. In fact, I've got to give credit to AirB. We've taken a lot of California low-emission vehicle program, LEV program and ZEB program, and we simply adopt California program. We call it, instead of California LEV, we call it OTC LEV, Ozone Transport Commission LEV, with some modifications. So you do a lot of good technical work, but we try to adopt that at a regional level. That's what we have done. We also looked at the issue of transport, transport of ozone and precursors over long distances, transport from Midwest and Southeast to Northeast, and how that impacts our ozone levels. So issue of understanding of transport of science, transport of ozone and NOx. We also have gotten quite involved in market-based approaches. We deal with 13 states sometimes under Ozone Transport Commission. So we look at, for example, how to control NOx from power plants from 13 states, tens of utilities, market-based approaches on that scale for NOx, very much like the SRES program for the federal program. And more recently, we are involved in regional haze, the whole modeling issue of regional haze. So every time the scale is larger than a state, we are generally in it. This is an example of what we're doing now, the climate change programs, what they call multi-state climate registry. And the person's name appears at the bottom, Heather Kaplan. She's our key person on that with her email address. And this is where we helping many states among ourselves, companies, the organizations, with respect to the registry of CO2, making sure the registry is transparent, the reductions are quantifiable, very much like what you're doing here. And in fact, at the bottom it says participating states. We want, with California input and our own, try to make a registry of the registry, so to speak, a super registry of all the states who want to play the CO2 trading program. This is the map of the states. The yellow ones are in. Massachusetts was kind of in, then out, and might be in again. Governor Romney last moment decided that they were not going to do the RGGI thing, but with the new governor it might be in. I don't know yet. One mistake there, I think the Maryland is not in, even though it's color yellow. Pennsylvania is an observer. So that's you see how we have to work with many states. The states have their concerns and how to bring them together at a given time and how they change based on their own legislation. And for example, Maryland is saying they would like to join, but they want to do an economic analysis first of the implications of joining, and these are the reductions on power plants for CO2. My interest in the subject, I'm sure some of you have seen this report, came in 2001, and it's interesting, it doesn't say regional air quality, it says global air quality. And if the global climate change and regional air quality, you make the hybrid, it's the global air quality. It was a report done by the Academy, National Academy of Science in 2001. In fact, Mario Molina, who was a California product and then moved to MIT and he's back at UC San Diego, he was the chair of that report along with John Seinfeld, who was the vice chair. And it's really asked two very important questions. And I think the key in science is sometimes it's very important to ask the right questions, whether you answer them or not, but ask the right questions because at least you have a good start. And they asked two questions. The context was in their case, really how to support, make a case for long-term observations. If you're going to see the effect of global climate change, you want to do before and after. So it's the baseline data and the future data. But the question, the first one was, how can global air quality change affect and in turn be affected by global climate change? And number two, what's the effect of long-range transport? Very important to this state, especially transport over the Pacific. What we have done in this study is really answer only the second part of the first question. That is, how does global climate change affect regional air quality? And that's what we have done here. So there are a number of questions there in that, but we just answered only one of that. I put quote scientific scales of air pollution because quite often they're political scales. So you have to be careful about, what exactly is the scale of air pollution transport. It's a combination. It's local, it's regional, it's global, it's all of the above. And I wrote down some pollutants there. One good example there is mercury. If you notice, mercury shows up in local, regional, and national. And recently we have a mercury control program from coal-fired power plants in the United States, which kind of is based on the assumption more or less that it's all global. It's all coming from China, so to speak. But there's quite a bit of mercury. Mercury is not one thing. Mercury is local, regional, global, all at the same time. There's oxidized mercury, there's elemental mercury. Oxidized mercury is regional, not global. And so a lot of mercury you produce just goes in your own backyard, so to speak. So you can do quite a bit about that part of the mercury. So we in the NESCAUM, with our role in science and policy, have chosen a very different approach than EPA. It's not a market-based approach for mercury. It's simply what we would call old-fashioned command and control, but it's really a performance-based approach, saying all power plants can control mercury cost-effectively in a substantial manner in a short period of time without really increasing the cost of electricity in a big way. I mean, that's a major finding, even though it looks pretty simple. And what EPA is going to do is to do not much till 2018, which is, what, say 11 years from now. And mercury is cumulative. It just adds on and causes all kind of problems down the road. So we are going to control mercury in our part of the country more like by 2007, end of this year, and next year in 2 steps with some flexibility, but not too much flexibility, just because mercury is toxic and it's got problems. So I think it's key to remember, the last one, that CO2 is global, but what you got to do still is to do at a local level and regional level, because the impacts are taking place also at the local and the regional level. This one you may not be able to read, but this is a very interesting issue, is very timely. Only a month ago, the U.S. Supreme Court, essentially state of Massachusetts has taken, or Commonwealth of Massachusetts has taken EPA to court, saying that CO2 really is a pollutant in the meaning of the word, the Clean Air Act, and EPA has the authority to control it. So they gone to the court, and before the court listens to you, these are the oral arguments you can find on the website. You have to show that you have a standing, that you are before the court because you have been injured in what they call particularized injury manner. I'm not a lawyer, but I got a couple of children who are becoming lawyers, so you can learn these things. But anyway, it's kind of interesting dialogue. Justice Scalia saying, I thought that the standing requires imminent harm. If you have not been harmed already, you have to show the harm is imminent. Is the harm imminent? And the attorney for Massachusetts, Mr. Milky, he says, it is, Your Honor, we have shown that the sea levels are already, he used the word occurring, but he meant rising, from the current amount of greenhouse gases in the air, and that it means it's only going to get worse. And he's interrupted by Justice Scalia. He says, when? I mean, when is the predicted cataclysm? And that's the thing about the global climate change. And Milky says, well, Your Honor, it's not so much a cataclysm as ongoing harm. The harm does not suddenly spring up in the year 2100, like we would do our modeling here. It plays out continuously over time, and even to the extent you're focused on harms that occur in the future, there's nothing conjectural about it. Once these gases are emitted into the air and they stay on a long time, the laws of physics take over. And later on this oral arguments, Justice Scalia does say, well, I'm not a scientist, and it kind of shows. And then, and this is the interest too. Later on in this argument, Mr. Milky says, Your Honor, essentially saying there's effect on ozone at ground level. It's not just other things, but the planning purposes, ozone goes up too, and which is what I will show later on. And finally, I mean, I did the counting. the word uncertainty, we know in science and policy, we always say, oh, things are uncertain, they always are. You know, the word appears 39 times. And you go through the dialogue, and it appears in the context of Justice Roberts saying the studies that are being developed to reduce the uncertainty. Later on, Milky says there will always be scientific uncertainty. And then there's argument about when we control lead and gasoline to lower lead, there was uncertainty there too, but Justice Roberts thinks that wasn't as bad as the uncertainty of effect of global climate change or CO2 on future climate. So you say, well, those are two different kind of uncertainties. And then finally, you know, EPA Solicitor General says, now is not the time for EPA to exercise such authority in light of substantial scientific uncertainty surrounding global climate change and the ongoing studies designed to address those uncertainties. So the point is, you know, at very high levels in this country, science and policy and law, people are trying to figure out what exactly the global climate change is and what's the level of uncertainty. When do you make decisions? When do you not make decisions? Cost of making decisions, cost of not making decisions. So there's a lot goes on. Frankly, this could be very important where EPA, if the court decides that EPA may have the authority to control CO2, and CO2 is a pollutant, and Clean Air Act allows them to do it, then on a national scale, things could happen. And maybe the justice should have read this thing, this great quote from Aristotle many, many years ago. I always show this when I make presentations. It's like, it's the mark of a smart mind or instructed mind to, you know, to not go for total precision and be comfortable with the approximation of the truth. And that's where global warming comes in. You don't know all the answers. And frankly, this is also export from California. Many of you might know John Hurt, teaches at Berkeley, wrote this book, Consider Spherical Cow. And he wrote a second book, Consider Cylindrical Cow. So I guess he's into geometry of various kinds. But essentially the point he makes is that a lot of environmental problem solving can be done, not without very fancy mathematics, but if you have a good idea what the problems are. And the word spherical cow, it's kind of a joke. If you, some of you I'm sure have the book. It kind of starts this way. It's a joke about theoreticians who first, it's the milk production at a dairy farm. They, you know, think about cows, a dairy farm. Milk production at a dairy farm was slow, so that the farmer wrote to the local university asking help from the academia. A multidisciplinary team of professors was assembled, headed by a theoretical physicist. And 2 weeks of intensive on-site investigation took place. And the scholars then returned to the university, notebooks crammed with data, where the task of writing the report was left to the team leader. And shortly thereafter, the farmer received the write-up and opened it to read on the first line, consider a spherical cow. So you kind of make approximations. You know, you don't have to, cow doesn't look like a sphere, but pretty close. And if you're trying to figure out what the milk volume is, you start that way. And I think the concept is that spherical cow approach to problem solving involves stripping away of all the extra detail. If you can get first-order issues figured out so that only the essentials remain. And of course, you know, your cow, which is spherical to you, is sometimes sacred to others. So you got to worry about how to bring many people together. But try to make approximation of a problem, knowing you can know all your mathematics and all your differential equations, but still try to see what the first-order issue is. And I think global warming is in that department. You've got to know what the big first-order issue is. I recommend this book. I'd say it's not as simple as it sounds. Okay, now with that warm-up, I'm going to tell you what we did. Here is the map of the U.S., and we divided U.S. into 5 regions: West, Plains, Southeast and Northeast, and of course Midwest. And the purpose, again, as a mission, was to look at this geometry. It also has Canada and also Mexico, the border states, to look at this area and say how the meteorology is now, how it will be in the future, and you drive your meteorology on that scale from the global models, models like this at Columbia, and downscale from the big scale to the little scale. And at this time, we're not done with this work completely. We have done 3 summers of 2000, 2001, and 2002, and that's for ozone. Ozone does change, so the episodes are different, so we have 3 summers. But we only have 1 full year, 2050 in the future and 2001 in the past. and we're still trying to do all kind of modeling. It's very labor-intensive and very computer-intensive modeling, as many of you would know. So we kind of, what I'm showing you is based on 3 summers of work, past and future, and one full year for PM. PM statistics tend to be more stable than ozone does. And some of you who are not modelers, I used to be, and all kind of tools here. We have essentially taken the GCM, which is the general circulation model of the Columbia University, for the historical and the future, run it through what we call MM5 mesoscale model, which kind of takes the big meteorology and makes it into regional meteorology. And then you have emissions, which I'll show you more about how we predict emissions in the future, which is kind of an art by itself. And then this MSIB processor, which kind of takes all the raw data and runs through this another model, SMOKE, which is the emissions model, and then the CMAQ. CMAQ is the Community Multi-Scale Air Quality Model. I'm sure ARB uses that here too, and we do. And the DDM, which is very great work by Ted Russell himself, the direct decouple method. The beauty of that DDM is not only solves the concentrations, but also tells you how those concentrations change as a function of emissions, calculus the derivatives. So you kind of know how the world will respond as emissions change. And so here's the meteorology part, downscaling. I already mentioned that to you. You take 4 degrees latitude and 5 longitude into 36-kilometer grid. That's, as I said, an art by itself. So I won't tell you all the magic because some of it I have not done. And I think this I can skip. And again, we wanted to make sure what we were doing was reasonably accurate. So the experiments are done from GIBS, which runs the global climate change all the way from 1950 to 2052, over a 100-year period. And within that period, our 3 years of 2000 are embedded, so are our future years. So we're trying to make sure our meteorology is consistent with the larger one. Emissions, I want to spend some time because a number of our people at NESCAUM worked at it. It's hard to predict emissions 2050. It's hard enough to predict in 2018. EPA has done a pretty decent job of 2018 and 2020 inventory for the whole country. We've done some work in that department too, but going from 2020 to 2050, how do you really know? And you don't make, maybe it's not emission projections as much as scenarios. Just think this is what we think will happen. What we did then, it's like almost like going to the Mars. You go to the moon and then you jump. So we kind of jumped to 2020, saying this is reliable data for EPA. And then from 2020 to 2015, there are all kind of approaches. We took this approach from Netherlands, image model, and they have this world divided into 17 regions. U.S. is one by itself, Canada is another, Mexico is part of Central America. And they have a lot of growth factors thinking what will happen. Close to the IPCC A1B scenario, people who do this kind of work. So we took A1B scenario, looked at the growth factors, and applied that to the U.S. and Canada and Mexico where we could. It's better to do here. It's easier to do it from United States. But Mexico, it wasn't that straightforward. They don't have projections for 2020. So we have to go all the way from 1999 to 2050. So it's not as accurate, I would think. Canada is okay for area sources and mobile sources, but not for point sources. They have confidential information. So you go through all, inventory is a can of worms, with many people would know. It's also a very important thing to do. So we try to kind of, it's like a mix and match. It's a hybrid approach. So we have emission projections for 2050 and then from 2001. I think I mentioned that. So CARE, the EPA's Clear Air Interstate Rule, their projections we took. And I think, again, we didn't do any creative work. And the point was we took what everybody else had done and make the right decision making. And this is the famous IPCC scenarios with A1B and A2Bs. People see that, how the world would look like according to IPCC, what they call sustainable and equitable future and kind of bad future, fossil fuel future and technology-driven future. So they have all kind of things can happen. If I can find this. So you see there's a lot of variation. We took this red line, the A1B, and it tells essentially that for carbon dioxide emissions are going up and won't go down until later. SO2 is different because there's a lot of action going on with respect to scrubbers in this country and other places and even in China. So the SO2 will reduce because there's technological solutions. CO2 just keeps on going up till later. And again, as I said, basic strategy was to kind of figure out the full year of inventory. And this is what we had to deal with. There are all kind of models. Everybody got an emission estimates from EPA. It's like, I think you were right that I'm going to have trouble managing this thing. Yeah, this EPA CARE, Clear Skies Initiative, even we had done some work. But in the end, this RIVM model is what we chose because it does make predictions till 2100. And it's very international in scope. So we took that. And that's the RIVM. You can see the United States, a region by itself, and Canada and Mexico. Okay, now here are the results. The first results you see there are with respect to temperature. So before you go anywhere, you want to see how good you are predicting temperature. And what you see there is 4 bar charts. I'm having trouble with this thing for some reason. Yeah, I'm trying to get this. Oh, there it is. If I can stay. Okay. So you see 4 bars, and they are observed. Yes? Yes. Oh, this would be great. Thank you. Yeah, this is so wonderful. So you got 4 bars, observed, predicted, observed, predicted. The first ones are for 3 summers together. The last 2 are for the whole year. And it's, it's averages of the averages. You're trying to see, are you okay in the main? And we do a pretty good job of the temperature by region, West, Plains, Midwest, and the whole U.S. here. First are summers, and then, of course, the annual should be lower. A little bit of cold bias, a little bit of warm bias, but still very manageable bias. One place it doesn't look too good is southeast. I mean, we predict more than, I guess, 1.4 degrees. So that's, again, it's not as wonderful, but that's the best we could do it. One could fix things, and we are not fixing it. We're just trying to see what the model shows before. And it's very hard to understand a lot of this interpretation on a larger scale, unlike regional models. So a lot more is going on. And the next one, after temperature, what we do, ozone and fine particles. And I want to spend some time here because this is what, again, the 4 bar charts, 3 summers together and 2 years together. First thing, you want to see that ozone we are predicting higher, about 15%, by region, by U.S., and that is, when you just look at the top, the reds are always kind of higher, and even on a national basis, some places we do not as good a job. And so that's what's first thing. When you look at PM, the blues are generally lower, and lower for the whole country. We are under-predicting by about 30%. For PM2.5 by region and by the country as a large. And one could, I guess, we don't do as good a job predicting lower concentration. Model just predicts higher when the value is very low, and that could explain why we are off by about 5 ppb. For PM2.5, I mean, people who are in this field, secondary organic aerosol, the carbon part, I don't think we've done a good job as a country, as scientists yet. The CMAQ model doesn't do as good a job. I think we are off. We could fix it, by like sometimes just kind of upscaling, but we're trying to figure out what's going on by region, by temperature. And so it's 30% off, so to speak. One explanation of many would be isoprene. This is SAPRAC model, which does not have isoprene. Isoprenes are supposedly, I guess, making quite a bit of secondary organic aerosols, more than we thought. The vapor pressures are sometimes underestimated or overestimated, so we don't condense as much organic aerosol as happening in the real world. So there are all kind of explanation, but this is our basic evaluation. Going to the next important thing, the meteorology. Again, the thing is, how good are you with respect to, again, temperature in the future? Now it's saying how the model says emissions, the temperature will look like in 2050 compared to what it looks now. And look here, these 2 curves to naked eye don't look that different. It's, what we are doing here is 1 year in the past, 1 year in the future. I think it's 2000, 2050. go the next one. Now we put 2 years together in the past, 2 in the future. And this is what the, by the way, I should explain. CDF is the cumulative distribution. So you're saying how much temperature below a certain number. And the scale is in Kelvin. And so this is for 3 years together. And kind of looks pretty, but here is really the kicker. You take the 3-year average in the present blue and 3-year average in the future, and you see the difference. That's the delta, where the CDF, or cumulative distribution function, is saying the temperatures are going to get hotter when you look at 3 years now and 3 years in the future. And that small delta makes all the difference. And just to make that point, you put the same 3 years, now the U.S. map and Canada, and what you might see to naked eye, if you're paying attention seriously, Texas is getting hot. And there's a lot more orange Texas in the future than here. Same thing with southeast. So there are places in the country where the temperature increase would be higher than the rest of the country under global climate change. And even cold states, I'm sure they would be thankful. Minnesota is getting less warm, or getting warmer. So you see changes. It kind of pushes up north and in southeast. One could see the same thing with humidity. And humidity is important when a lot of calculations in chemistry. And humidity is about, it goes up about 10 to 20%, depending upon where you are. And I have not plotted 3 and 3, but you can tell these are 6, and I could have taken averages and find, again, humidity does change. There's more rain, and I have a rain plot too, in southeast, and that has effect on chemistry. So, and then you say why certain areas show a certain behavior, not others. And finally, rain, which is really the surrogate for cloud cover. And you find the rain has, see this area is more orangish here, and the scales are at centimeter per hour, which is kind of funny scale for rain. People think of inches per year, but you can normalize it centimeters per year. And you see more rain here, and you even see more rain in the Great Lakes area. And rain, besides scavenging, also has indication of cloud cover, which is indication of photochemistry. And so you see, in fact, Chicago seems to perform better in the future, as I would show you, just because it might rain more often there in the future. And back again, I'm sure you're going to pay attention to California and the West, but this is our inventory in 2001, 2020, 2050. And this is for NOx, going from 20 million plus tons to this in 2050. The color of the state is indication of total NOx emissions going down in California to some extent. And Texas was very dark, but not so dark in the future. So, and this again, projections of our emissions for different parts of the country, for different pollutants. I'm just showing you for NOx. And this is interesting by itself. This is for the whole domain. One thing I have not said clearly, we've done this thing. 2001 is the present, so we know what that is, the average of 2 years or 3 years. But then we have 2 futures. We have 2050 under climate change and emission changes, emission reductions or increases. And then we have only climate change. If nothing happened, we just stay the way we are in 2001, and climate took over, so to speak. Emissions still change, but not as much. They change because of temperature and biogenics as a function of temperature. They change. And this is what it shows. Even in the absence of emission reduction, the hydrocarbons, mostly biogenics, go up by 15%. But when you put your controls together, for this part of the world, NOx emissions go down by 50%, SO2 go down by 50%. This is the federal program for SOx and NOx care. VOCs don't go up much. In fact, the net effect is just as wash. It's plus 2%, because biogenics go up, anther go down, but the net effect is essentially very close to not much. Ammonia emissions go up, and that has its own consequences, about 7%. And to this one we're doing for Canada. Only interesting thing there is the PM10 for all kind of construction activity goes up. Even Mexico, emissions go up, not down. So a lot of control programs, if you notice, CO, that's the first to CO, but NOx goes up from here to here. Even SO2 goes up. So that tells you, again, the future of different countries. This one is very busy, but I need to make some points. And what I'm showing here is changes in pollutant concentrations in future compared to the historic values. What you have is a lot of data for summer, because ozone is important for summer, and then a lot of data on annual basis. First you have for ozone, then you have for PM2.5, then the parts of PM2.5, sulfates, nitrates, ammonium, and organic carbon. Then we have by region, Western Plains and Midwest and Northeast and so on, and the whole United States. And I think you won't be able to see it, but I will speak a few things, and you want to see what I think we found. For summer, if you just look at the summer on the top, and under just the NP scenario, what we call just the global climate change scenario, no emissions changes, just the climate changes, the temperature, humidity, and a little bit of biogenics. Under that scenario, it has a small effect on future summer, the value we know, the maximum 8-hour ozone average over the U.S. And essentially, this number on a national basis, it's a wash. But then you start seeing changes. Ozone can go up or down by 2 or 3% depending upon where you are for the average of the maximum 8-hour ozone. With respect to PM, they go down by about 10% just in the climate change scenario. It's the more rain, more scavenging, and you see some effect of that. So those are 0 to 9%. And then if you look at summer and the combined effect, which is this thing, climate and emissions, you see for summer, for ozone, you would expect changes. We are reducing emissions. So the NOx, sorry, the ozone goes down by about 19%, and southeast has a larger decrease for ozone. For fine particles, sulfur and nitrogen reduction going down by about 35% for summer. Within that, sulfate going down by 50%, nitrate going down by 65%. So you see the effect of emission reductions under climate change in the future just because of substantial emission reductions going on. That's on a summer basis. If you look at the bottom numbers here, the annual, first just the effect of the global climate change alone for ozone and PM, and it's slightly different over U.S. in the year 2050 compared to 2001. The sulfate fraction, organic carbon fraction, they're higher while the nitrate fraction is lower. And one explanation is the higher VOCs and SOx emissions in a warmer climate, although the same inventory is used. And if you look at, again, the bottom, the annual combined effect of both climate and of emissions for regional PM2.5, the effects are more pronounced. The annual average U.S. concentration for PM2.5 and the 8-hour ozone, they're about 23% and 9% in that range lower compared to 2001. And you're expecting, and you're showing large reductions in sulfate, about 31%, nitrate, about 48%, and ammonium at about 32%. So there's a lot of explanation. Some of it may not be totally confirmed. I mean, we're just still looking at the results and saying, what this means, especially by region. And this one then comes down to the real, cities like Los Angeles. When you start looking at the bad situations to begin with, Los Angeles, Houston, Chicago, New York, and Atlanta, big 5 cities in different parts. And what you're seeing there is number of days over 80 ppb. This is for 3 summers together. And it's not maybe exactly right what you find in LA, but this is the model predictions in our base case. About 150 days of over 80 ppb, 50 days a year, so to speak, in the present. And when you come here under just the climate change, and emissions change only because temperature changes, you may have, instead of 150 days of exceedance, about 220 days. So that's getting worse. You think the peaks are not good. A lot more days. Even Houston, 130 to 168. Chicago is going down. And that explained, again, the rain and lower chemistry. Atlanta, from 199 to 195, much more of a wash. New York, increase. So it's different. I mean, that's the key point, that the ozone peaks are not going to respond in some kind of average sense. It's place by place. And just the climate alone compared to the base case, there are large differences. And also the peaks, going from 119 in LA to 146 parts per billion. And you see the increase at 20 to 30 ppb. So the peaks will go up, And people, others, not us, Loretta Mickley at Harvard, and they've done a lot of good work on that episodes when they would occur, they would last longer because the frequency of the cyclone event won't be as much, and once they come, they stay. So not only going to have 2 days of ozone, you may have 6 days of ozone peak. So that's not our work, but that's their work. So peaks go up, number of days of ozone go up for most of the area. And again, to show the same thing on the U.S. map, this is now, the point I'm going to make in a minute is that this is the ozone in the present, the future, you subtract the two, and the difference, the scales is about minus 6 ppb to, I think, 1 plus ppb. And you see some ozone disbenefits on an average sense. You know, you see some red dots if you have sharp eyes, or you can look at the scale on your computer with the finer scale. You see some red dots, some ozone going up. But the point here is when you subtract the future with emissions and climate, from that you subtract just the climate, these two plots look the same. It kind of tells you whatever we're doing, the changes are taking place on a global sense or in a national sense, not the peaks, by emissions. Emissions are making a difference. That's the point we're making even under climate change. What we are doing is still the right thing to do. I mean, that's the point from a policy angle. Same thing with PM2.5. You take the present, the future, subtract, and then subtract climate from climate and emission, and these two look the same. And again, the point is emission reductions are doing the hard work. Okay, now this is the DDM work, the direct decouple method. It's not only saying the emissions are ozone is changing, but how does it change? How does it respond to the reductions in VOC and NOx? So the top one is ozone with respect to anthropogenic. Remember, this was concentration change as a function of emission change, the gradient of that. And west looks interesting. The red goes up big time, but other parts of the country look more or less the same. That is, it's sensitive now, it's sensitive in the future, more sensitive in the climate, but you are in the right direction. I mean, you would worry when some of the sensitivity changes direction. That is, what you're doing may not work in the future because of climate, but this one says it's more or less sensitive but still works in the right direction. Also says, with respect to ozone, that it's more sensitive to NOx than to anthropogenic VOCs or to biogenic VOCs. I mean, these charts, the magnitude here in ppm or ppb is about 1/3 of this. So you're still doing better with overall NOx control than you would do with VOC control. With respect to PM2.5, it's always more complicated because it's not one thing. So this one is telling in the United States and the Southeast, I don't have a map for the West, but the sensitivity of sulfate to SO2 itself, to ammonium, to NOx, anthropogenic NOx, and I think the interesting thing here is this little negative and this little negative, and essentially what we kind of know, and which is that when you do cut down, especially it's pretty important in the East, when you cut down SO2 emissions, your PM2.5 does not go down proportionally because it's the chemistry competition between ammonia and sulfur dioxide and nitrogen oxide. You cut down SO2, ammonia just finds nitric oxide, so ammonium nitrate goes up. It's what is known as like a nitrate replacement effect. It's about 1/4. So for every 1 unit decrease you should see, you might see only 3/4 of it. So the nitrate picks up. So it kind of confirms it, which is a good thing, at least. And then finally, the last part, you know, you can do all this work, and you say, well, how do you really know? I mean, how accurate you are? And that's where the keyword comes in, the way I use it, not the way Supreme Court did it. Uncertainty. I mean, how do you figure out, how do you look at the results of uncertainty? And here, the MIT people came to our rescue, and they've done this, instead of the GIST, a 3-dimensional model, they have a 2-dimensional model. It's kind of very sharp, and it can do a lot of scenarios just because it's 2-dimensional. So they have this temperature distributions, how not only temperature would look like one realization, but hundreds of variations, just like a Gaussian curve. So you look at the whole distribution of temperature, look at the whole distribution of humidity, and after taking that, and this is the IGSM, the Integrated Global System Model. Once you use that, you kind of lose the conservation of mass. So we had to do all this runs all over again. So you take a 50% case, we take the extreme, the tail end of the distribution, 0.5%. It's like 2 and 2.7 standard deviation. And the high extreme, you go to 99.5%. So look at temperature distributions there at the tail end of future realizations, and run this thing again and say, okay, if I'm not accurate, and if I'm really in the tail end of the distribution, how the ozone would look, and first how the temperature would look. So this is what I was showing you earlier. This is the 0.5 percentile, 99.5 percentile, and then you subtract the two just to see what's going on, and subtract this from the middle. And what I want to show here is this part. And again, the scale is in temperature in Kelvin. And what you're saying is that where these temperatures are being predicted with a higher level of uncertainty. When the temperature is hot, you're making a larger error. It's the plains and west. So the temperature prediction there is not as reliable, just by looking at the MIT's work. You go to the same thing with humidity, and you find out again the upper middle, which is the extreme end, that's where the uncertainty is higher. And then you take that and you run this future of 2050 under three scenarios, the middle, the lower, and the upper. And because it's hard to see, so you subtract. That's the way the naked eye sees the difference. And essentially making the case that this number, which is about, I think it's 6 ppb minus to 6 ppb plus, you see changes here. Results here are not as reliable. That's the point I'm trying to make. For ozone, same thing for PM2.5. And again, you extend that to see what's the consequence of that. Timio said Georgia Tech used the word megacities. I don't know if some of the cities are megacities like Mexico or Tokyo, but I guess megacities are big, big cities like, so I don't know, Atlanta is a megacity? I don't know, but he lives there, so he thinks it's megacity. But anyway, the point here is when you look at these cities and you do what I call, you know, what will happen more often than not, the mean, the summer of 2050, the low end and the upper end, see Houston. What it's saying is, if you think in Houston, the number of days over 80 ppb, the medium case is 10, but the extreme case, it could be 24 days. You could have a lot worse situation in Houston under what we have done compared to, say, Los Angeles, where 6 days might go to 7 days under the worst case, 4 to 6 for other areas. But Houston, also the peak goes up. So where you are able not to predict your temperature accurately, and you kind of hope, not hope for the worst, but you at least model for the worst, it could be bad. So I'm coming to a conclusion and just kind of leave you with some simple thoughts. I'm on schedule? Okay. Okay. I was, but I have to go to the last plot. Okay. The first major point, I think, when you kind of look at the effect of climate and the emission changes we are making in this country and Canada and Mexico, under that scenario, the ozone in the future and PM concentrations in the future over the U.S. are expected to be lower, but the effects are more pronounced on a regional basis. So you can't just do the U.S. thing. You have to look at what's happening in different parts of the country. The organic carbon, just because we're cutting SOx and NOx, big time, 50% so on under care, the organic carbon is going to come back. That's going to become a big part of the equation, more than what we think now. And we don't even understand it today well. So just imagine in terms of science, that becomes a big part, and we haven't figured out all the chemistry and the aerosol thermodynamics of it. So that could become a kind of science issue. Regionally, our part of the country, eastern U.S., it's going to have, I think, more benefits than the other regions. And just because the emission, how the math works out. And the fourth one, the NOx controls, the anthropogenic NOx controls you're doing here, a national program for automobiles, for power plants, for industrial boilers, and so on. It is important now. It's going to be important in the future. And I think it needs to continue that way. And you're not going to see larger benefits because of VOC reduction, just like we don't see now. So that's confirmed. And then uncertainty, the last few slides, the work we did with MIT, what you're predicting for ozone and PM and the uncertainties associated with those concentrations due to climate change are really high in the high extreme case when I was showing you for 99.5. So you have to pay attention to that thing. That is, things where they're bad, like in Texas and Houston, they could even be more bad, so to speak, or worse, more so than here. And also those uncertainties due to climate change are not, there's no national average. It's regional in nature because how much it rains or doesn't rain, the temperature. So Houston could, as I mentioned, and areas like that could be in for some bad uncertain times. And finally, the controls themselves, they have larger impact. Now, I would give you an order of magnitude. What we call PRB, policy relevant background, how ozone historically has gone up. If you kind of look at the post-industrial, it's from 20 parts per billion background of ozone. We are about 40 these days. So this extra 20 is just the man-made activity of emissions. So when you compare that 20 extra ppb and policy relevant background caused by human emissions to what the climate change would do. If you saw the first chart in the beginning, I said ozone, it's in the climate change, ozone may go up by 2 or 3 ppb. So it's going to go up 2 or 3, maybe 4, just by climate change. So compare that 2 or 3 to 20 ppb by emission. So I think that's what the model, that's what the results are showing. Climate change is going to have an effect. Ozone is going to go up in some places. But the PRB itself, the policy relevant background attributed to emission changes historically, is much larger. I thank you for your time, and I'm sure there are questions. The system works out. People send an email or?
There will be emails coming in and questions here.
All right. Kathleen.
Please use we have a microphone so that the people on the webcast can hear the questions.
Catherine Phillips with Environmental Defense. Praveen, thank you for this presentation. Thanks also for recommending yet another book to read, because I've read your recommendations in the past and they've always been worthwhile.
I've been marketing books and I don't even write them.
It's true. I have two quick questions. The first one is, when you're talking about the increase in PM 2.5, can you go into that a little bit more, what you're talking about, because I'm having a hard time grasping why we would see an increase in 2.5.
No, I said the model is, in the beginning, just the baseline model was under-predicting by 30%. That's just the evaluation. The model wasn't doing as good a job as the real-world data shows. And explanation of that was that we haven't figured out how to do the chemistry and thermodynamics of fine particles like we have done for ozone. So that's one thing. But in the future, once you cut down SO2 and NOx emissions substantially across the country under the CARE program, then the sulfate fraction, nitrate fraction, and therefore the total PM 2.5 will go down. I mean, that's the point I was making.
Okay.
And I think that's what I was making, unless you saw something.
No, I was looking at the last point, on the last slide, the 0.3 or 0.2.
It's done? Last slide, where? Maybe they can bring it. Oh, okay. The third
organic
point?
carbon become...
Oh, okay. No, I think the point I'm making there is that PM 2.5, the major components of PM 2.5 are sulfates, nitrates, organic, elemental carbon, crustal material together, and some water. It makes about 100%. Sulfates in the east are about 1/3. What's not appreciated, even in the east, when you look at organic carbon in places like New York and Boston, the organic carbon is about 50%. I mean, half of the PM 2.5 is not sulfates and nitrates. It's the cars and the diesel, so to speak. So, but when you take that out, your overall emissions go down. Overall PM 2.5 goes down, but the organic fraction of that, because we really haven't not done much, and there are biogenics, so that fraction will become important. The point I was making was, if that is the case, and we still don't understand organics too well today, so we're going to have the situation where we're going to look at concentration and say, well, what's causing it? And then our understanding, chemistry and physics, I think would need improvement. That's the point I think I was making.
Got it. Thank you.
Dane.
How did you deal with elemental and black carbon? And I didn't see you mention either of those in your modeling.
Organic carbon was mentioned, and SOA.
Elemental or black carbon?
Elemental carbon is not mentioned, and we haven't shown the data. I would think the elemental carbon as a fraction of the carbon overall, the total carbonaceous material, is what, about 4 to 1, 3 to 1, depending upon where and when. And PM2.5 strategies, that's where the elemental carbon shows up. I mean, essentially that's where it is. I don't know there are any strategies for PM2.5, including there's diesel retrofits going on, but there's no national large-scale strategy saying, like we do for SO2 and NOx and even hydrocarbons. Elemental carbon is, I think, more ad hoc. I mean, I don't know here, but I'm sure here too in California, we have this big efforts on retrofitting trucks or construction equipment. But there are 100 here and 20 there, but you're talking millions of trucks and millions of construction equipment. Yeah, you'd think so. It's back to the global climate change, yes. No, not here. I think because we're looking at PM2.5 and ozone and looked at carbon only in the context of PM2.5, not in the context of climate change, which is a separate issue by itself. Am I supposed to read these questions at the same time? I guess okay. Pardon me? Oh, I should talk loud. Okay. So I'm learning at the same time you guys are, okay, right? So I'm concerned about local regulatory solutions that inadvertently drive industry to other countries with less environmental regulations, that is, a lower cost of operation where net emissions are actually more harmful on a global scale. Because we live in a global economy, this concern has already become a reality in the production of most products that we use on a local scale. For example, the production of metals for hybrid car batteries is likely sourced to places like Africa and Southern America. In your opinion, is it effective to create local regulation, even if just by way of example, leadership, if this local regulation will force more carbon emissions from sources such as China and India? By effective, I mean the reduction and control of global carbon emissions and other greenhouse gases. How do we effectively accomplish this? And if we do not make the most stuff, and hence can not reduce emissions of the production of stuff? It's a hard question. I mean, this is from a gentleman named Aaron Johnson Karras. I think the whole point about global climate change and the policies has been to do things on a global scale. I mean, carbon more than any other thing is global. Mercury, as I mentioned earlier, was global and local, and you could do things locally and not simply, talk about global. Here, I think, whether it's California or the East or the world at large, Kyoto Protocol, post-Kyoto Protocol, who is covered, who isn't covered, what everybody's timetable is. So I would think carbon strategy should be on a global scale with all the other things going on in globalization. There are other large driving forces about where the jobs are, where the production is. You would expect carbon not to kind of make things better or worse in that department. That is, you apply it across the world. I mean, that's my best, I guess, technical answer. I'm not a political type person, so I won't say it. Go ahead. Law of cleaning technologies for carbon?
I'm just wondering, in terms of reducing carbon dioxide emissions, if every plant reduces complete emissions by 20%, it seems like you get a 20% reduction in each of SOx and NOx and in carbon dioxide, for example. Whereas if you are putting in certain cleaning strategies, you might be able to get 80% reduction of SOx and go up in carbon dioxide. What's the balance?
Okay, the balance, that's a very good question. I think we, as a advanced society, we have figured out what to do about SOx and NOx and mercury and other things. Sometimes we have long arguments in this country about how much and when and how much it's going to cost, but SO2 is not rocket science. So you put scrubbers and you can control and effectively. Same thing with oxides and nitrogen. Same with mercury. But carbon at this time, I don't think there is a apparent technology fix. The carbon sequestration, capturing carbon is not cheap. Collecting carbon and then storing it is not cheap. So I think, I think that's it. CO2 is a very stable oxidant. It's not a stable product. It's not easy to scrub like SO2 is in NOx. So that's one thing. we are trying to push what's known as IGCC, Integrated Gasification Combined Cycle, which is a carbon-friendly or carbon-ready technology. That is, if you're going to build new power plants, which is happening in this part of the country, a lot of it, not in California, but outside, we are still building power plants the same way what engine was, maybe a little better, but not the 33% efficient. They still burn coal the same way, simple Rankine cycle, nothing, you know, thing I learned in undergraduate school 40 years ago, 30 years ago. So you could do much better, for at least for new power plants. So I think that's one way. That is, you know, you do the right thing right from the beginning instead of what's being proposed. I don't know. Like in Texas, they're proposing an 11 or 19,000 megawatt of coal power production, just like the way they did in the 1950s, because they want to get into the baseline, as I understand. So you got more CO2, so you get more credits. So you have to. That's one area. I mean, of course, there's the transportation sector where you can do a lot more and a lot better things than we are. So I think the carbon is not going to be easy. In terms of the technology. But I don't know, I heard the other day from one of the environmental folks, he had this slide, he says, you know, we the human beings, we have monetized the cost of controlling mercury. We want to know how much it costs. You know, monetize the cost of saving the planet, and we figured out it's not worth it. I mean, that's the way we are behaving. You know, because somebody has to say the Stern Report. I don't know if people have seen the Stern Report in the executive summary, essentially saying that carbon is one where it's the best, the worst, or the most clear example of market failure. It's not working. People knowing what could occur in 2050 or 2100, it's within 3 generations. You know, when you kind of do this modeling 2050, and I remind myself I won't be here. But that's not the point, because people would be still here, and you want them to be here. And it's your children, your grandchildren. I don't want to give a speech, but the point is, you know, it's not a long time period. 2100 is almost here. So, and you can do things, but the market doesn't seem to respond to changes which are subtle. You saw the Supreme Court, you know, when is the imminent cataclysm coming? So we kind of don't see when things are not getting worse tomorrow or next year. And this is one of the situations where it's going to get worse over time if you look at all the data and listen to the scientists who are a lot smarter than I am. Yes? Hello.
Going backward to your modeling, and probably a much more trivial point, but one that bothers me particularly, is the CMAQ model is, you know, vastly less precise in the West than it is in the East. Is it possible that your conclusions
about West
are in fact similarly less, less trustworthy, I would say, for Western locations than for the East?
That's a good question, though I may not agree with the first premise that CMAQ is less accurate in the West. CMAQ got problems. I was in the peer review of CMAQ twice. I mean, we sat down, 6, 7 of us, and looked at the CMAQ in the inside and outside, and we wrote reports, which is on EPA's website. I mean, CMAQ has problems, but which model doesn't? But I don't know whether it's less precise in predictions in the West. I mean, do you know something?
Well, actually, outside of urban areas, it performs very poorly in the West, because it's got problems that are inherent, probably inherent to MM5 rather than to the CMAQ chemistry, in that it does not disperse horizontally or vertically the way the atmosphere does in the West. It seems to perform quite well in the Great Plains in the East.
Well, you know, we had trouble with the Southeast too, so I don't know. Maybe we can talk later on. And I had this impression that CMAQ had difficulty with organic aerosol, but seemed to be across the board. And it may be that there aren't, if you're comparing the evaluation, the baseline evaluation, there weren't many PM2.5 sites in the West. I guess there are only 100 PM2.5 measurements. So I think there's sometimes not enough data to compare against. And when you're saying something about evaluation, but it's based on very little measurements and making judgments, I mean, that itself could be part of the problem. I'm just speculating, I don't know.
Yeah, I don't think it's great enough to overcome the disparity you've identified between climate change versus emissions.
Okay, the larger finding.
Yeah, I think that finding is probably, still reasonable. I was just curious if you had considered that spatial disparity in the model.
No, we would. I think, to be clear, we are presenting the results still under construction. I mean, and there's a lot of work here, a lot more papers to be published, and I think there'll be a lot more findings. And there are a lot of other people besides ourselves. We were one group, UC Berkeley was the other group, Harvard was the third group, University of Illinois, Carnegie Mellon, Washington State University. So we're going to have this big meeting in February, in fact, all the researchers, and say, what did we find? And I think there's a lot more to be found here. I think things I'm stating may not be, that accurate 2 or 3 months from now once we go back and start looking. So I'm very careful making judgments at this time, and you may be right. Yes?
The degree of confidence one can have in modeling pretty much driven by the basic assumptions that go into the model.
Yes, sir.
And before I would look at a model's detailed output, as you have shown to us today, I'd like to know something about the basic elements on which that model is based, what assumptions were made, what population growth assumptions, what automobile miles per year assumptions, whether or not the assumptions are varied from region to region, as I assume they are. You've got an extraordinarily sophisticated model, that's clear, and you've got beautiful graphic representation of highly detailed database. But my question is there somewhere a publication, or is there on the internet a list of the basic assumptions that underlie the model that one could get to?
I mean, this work is going to be published soon, so there's going to be, more details and more English language and not just pretty PowerPoint. So I think that's where we have to explain how we, for example, emission projections. I think maybe a very uncertain area. We are not even making projections. I call it scenarios. And if you saw the A1B scenarios and other IPCC scenarios, they're saying it's not one future emission. There could be tens of these. We just took one, A1B, and perturbed around that. One could take 10 others and perturb them, and suddenly you got a larger number of runs. I think the only thing you can do about future emissions is to say, here are the possibilities, and what are the consequences of those possibilities, and the uncertainty of those possibilities, and what's the effect of that on the results of you. Very, very scientific way to answer it. Instead of saying, I really know what the emissions are going to be.
My assumption is your final conclusions say there is a range of possibilities in the future. Certain behavior moves us toward the bottom of that range, other behavior moves us toward the top of that range, and you can't predict with any more assurance.
Well, yeah, I mean, that's one way to say it. Saying here is our range, and here is the range as a function of what we know. And I think one thing we are saying is, at least for that A1B scenario, what we are doing today in 2020 and all the way till 2049 and 50, we are generally on the right track. It's like the first order my spherical cow example. I think we're there. That is, don't change things. There are always issues, whether NOx control is the right thing for or not. We've been fighting NOx control in this country forever. Whether NOx control was good for you or bad for you, and disbenefit, which I always claim, disbenefit is not a word in English language, but we use it all the time. Go and look in the dictionary, and we made a big deal out of disbenefits, and this country fought for years, EPA including, whether NOx control really was good for you or not. So I think certain things you have to kind of go beyond and say this seemed to work. California, frankly, the state has done an outstanding job, of doing the right thing, and we kind of look to California to kind of say, and not that you may be right 100%, but you generally are right in the right direction. Yes. There are a lot of questions on the email which I have not been reading so far, so maybe I should read one from, is that okay? Yeah, okay. Patrick Griffin. Were anticipated demographic changes such as population shifts between regions and countries considered as one input for the emissions portion of the model? I don't know, but I would think the answer should be yes, because the RIVM model from Netherlands, it kind of says how the world would look not only up to 2050, but up to 2100. So they kind of taking into account the A1B scenario or others, which kind of talks about world looking sustainable and equitable in one end, and the other end, I think, is fossil fuel and, I guess, energy intensive, and then there are issues of technology. So they have all kind of possible scenarios, and I'm hoping that within that socioeconomic factors they take into account where people live now and where they might live in the future. I would think. I don't know. Another question from Suleika Chatrapadhi. Hi. In your view, do you think that the prediction in PM formation is difficult because of the fundamental property of vapor pressure? Is a big uncertainty when it comes to estimating / measuring this quantity for semi-volatile organic compounds that contribute so heavily into formation of SO8. Thanks. I could not agree more. Yes. I mean, you'd think vapor pressure would figure out by this time, but the whole partitioning of semi-volatile, whether they become particles or they don't, and they keep on changing back and forth depending upon lack of equilibrium, it's a pain. And it's a large fraction of PM, about half, as I said. So I think this could be the size issue of the future. Maybe not as much as elemental carbon, but organic carbon, because elemental carbon at least doesn't react, and it's a small fraction. It's diesel and wood smoke. You kind of know where it is, where it goes. In fact, the IPCC model uses black carbon or elemental carbon as a tracer to see how things go. So it's kind of a nice pollutant to figure out. It's like lead in the old days. Lead was a good tracer. You knew where it was coming from. Now that lead is gone, a lot of scientists don't like that. I mean, they can't trace their automobile, so to speak. So, no, I could not agree more with that. Yes, go ahead. There was a question here.
Raphael with Environmental Defense. I have a question more for clarification. It's not as technical and doesn't involve chemistry, I don't think. Your last point on your conclusions is emission controls have larger impact than climate change, and I'm assuming that's a larger impact on pollution reduction, right?
Yeah, that's what I was trying to say. Yes, sir.
Okay, and then you also have a slide
on Houston.
Is that what it's?
Yeah, I think what I'm saying, when you look at overall, my statement is correct, but when you start looking at some areas and you start looking at peaks and looking at the outliers, where I was saying Houston under one of the scenarios could get worse in the climate change alone, when the number of days exceedance will go from 10 to 24. So the thing about averages is averages hide a lot of bad things. And so you have to look at the peaks, and I think that's the point I was trying to make.
Okay.
That overall emission reductions are going to be good. Climate change alone by itself wasn't going to make much of a difference, except when you start looking at the peaks, and except when you start looking at the peaks in the outlier case. Things could get worse.
Let me ask for some clarification then on this graph. It's your ozone concentration characteristics, the regional and local cities, predicted maximum 8 hour.
Yep.
For LA, it says that, if I'm reading it right, the three categories are current situation, 148 days of ozone, future scenario under emission reductions, no climate change, 31 days.
Yep.
Future scenario, 2050.
221.
Is that what it is? Okay, I can't read it.
Yeah,
But it also
it
includes climate change.
Yeah, I think what I was saying there was, if we stay as we are in 2001 and don't change the emissions but change the climate, then a peaker like LA, the peak value, the number of days when it can get worse would be bad, and the value itself would be bad, because emissions are not changing. Climate is affecting the peak values more than, when you show the whole average, when you average, everything, and not just 8 hour, but every hourly value you average, you don't see as much effect as you will see under climate change for places like Los Angeles, where the number of days would be more and the value itself would be more.
Okay.
So I think I should qualify, and I'm listening clearly what you said. That is, overall emission reductions are benefit, but if you look at climate change alone, without any emission changes, things could get worse in some places.
Is that what that last number is, 221 days? Does that represent no controls and worse?
Yeah, no controls, and the temperature goes up and humidity changes as it does, and and the emissions go up only with respect to VOCs, because they're a function of temperature biogenics. But you don't have a lot of biogenics in Los Angeles, I would think so.
Okay, that clarifies. Thanks.
Okay, thank you. That's a good point. Okay, there's one. Oh, go ahead. No, it's all right. Then I'll read this later.
Yeah, if I recall correctly, so right now you're still in the process of calibrating the model. PM2.5 underestimates by roughly 30%.
Yeah, about right.
You attribute that to isoprenes?
That's one of the explanations.
Inventory.
Yeah.
So my question is, just sort of, again, ballpark, what sense do you have of once you can calibrate more precisely to observed versus predicted, what the knock-on effect would be with the quenching in NOx, how that would affect ozone?
When you said NOx quenching, you mean scavenging or NOx?
The VOC, NOx quenching, they all interplay with each other.
I don't know, but I know the things we are looking at, and we are purposely not fixing it, because one of the problems I learned when you do modeling, our technology is moving faster than our thinking is. And we tend to go and fix our models right away, saying, let's do this and do that, and the results look good. But I think one of the recommendations we made to CMAQ people, before you change anything, first understand, because our mathematical tools, our computer tools, our visual tools have gone so far ahead than our mind has. And there's a tendency among us, including myself, to kind of fix it, and then you get the right answer, and then everybody's happy, but that's not. So I'm saying we've got to figure out what's going on. Isoprene is one. The other is this whole new debate, which came in the Science magazine, I'm sure you're familiar with, that came in at University of North Carolina, where he's saying the acid catalyzed reactions, the inorganic acid, sulfuric acid, nitric acid-based reactions are causing secondary organic aerosols, organic, to be a lot more than they are. So there's this very fast process that is you're getting a lot more organic because you got a lot more sulfur. And at least in smoke chambers that is shown. Is it true in the atmosphere? Under what conditions? I don't know. But you could easily go and fix the model to do that, and then get the right results. So we are not, and some people are questioning, including EPRI here and others, saying this may not be the real world situation. Like smoke chamber is not in the atmosphere. So I think that's the second one. And of course, this whole connection between inorganic and organic aerosols. I'm not the expert, but I see and I read and I talk to people. I think there's a lot more going on. I mean, hopefully in the next 2, 3, 4 years, people would be fixing models in the right way. So I present you, results which are, as I said, still under construction and just speculating, but not knowing whether this speculation is more important than that speculation. Yes? Well, I hope it does the second. And when you say model, and I wish it was just a model, you saw we got tens of these models. That's the complication. You got global models and regional models and in-between models. And I think that's a question you're raising, too. How do we really know? I would think the temperature is the ambient temperature predicted by the global general circulation model. That's very meteorology based on conservation of mass equation. But when you go into emissions and make projections of future emissions, I assume, especially the RIVM model from the Netherlands model, takes into account how people would live and what kind of temperatures they live under and what kind of air conditioning they will use, and therefore how much electricity would be produced and how much emissions because of that. I would think so. Yes, yeah. Because, in fact, that part is simpler because the Mobile 6, I guess, model takes into account the emissions, evaporative emissions as a function of ambient temperature.
I think Raphael has started something here because it got me thinking too. When you're talking about Los Angeles and Houston, clearly there are already places that have high temperatures, and there are already places that are having a very difficult time controlling criteria pollutants, controlling ozone levels. The San Joaquin Valley would fit into that same category. Would the research that this preliminary research, this preliminary modeling, would that suggest that we have to be more aggressive in our NOx controls, for instance, in our other criteria pollutant controls than we have been at this point in those targeted areas where we know climate change and the mix of climate change and pollutants is going to have an effect on ozone levels in the future?
If I understand you right, I thought you heard me say that I thought we should be just as aggressive, if not more so. I don't think we have to be less aggressive.
Well, that's what I know. Do we need to be more so?
Yeah. In that direction, yes, but not in the other direction, I would think, even taking into climate change, because if you look at the peak days going up under the non-projection scenario, just the climate change. So I would think yes, especially if you're handling the peaks.
So we need to redouble our efforts on NOx control in those areas?
I don't know about redoubling. You're trying to be quantitative. Yes, I would think so. More controls, not less.
Okay.
But again, the key thing would be how much NOx reductions could occur. How much more is left.
I'd like to thank Dr. Gene, for sharing this work with us, and it's so valuable to be able to project the future and the uncertainties in projecting the future in making our plans. Thank you very much.
Thank you.